Wait, that wasn't intentional?
No, that wasn't intentional, but I had intended to record it. Technically, everything we just said was already recorded, right? So it's not a big deal, but that's, I was planning to record this. All right, so if I look at this, right, AN and BN, these are the two basic equations that we have for determining Fourier series coefficients. There's a more formal proof that you can certainly go through to derive everything that I have here. But I think it's useful to think of it from a physical perspective, because there are devices, I talked about it, a device called a spectrum analyzer. It's basically that same thing I showed on my phone at the very beginning that basically does just this. It does this multiplication, does this averaging, and implements this, right, with circuits, right? Or in software. You can do the same thing in circuits, or you can do it in software, right? So these are the basic equations. And I add to this the sister equation of, if I have the complex series and need to figure out the alphas, it's very, very similar, right? And what I said last time is, it's my suggestion to use that one most of the time, all right? Because at the end of the day, even though it's got complex numbers, it is simpler math-wise, all right, to go through it, okay? So where we ended last time was with this waveform. Basically the waveform I showed at the very beginning. So where I have a square wave with a peak value of 2, all right? And he's repeating, right? He's repeating with a period t, okay? So I said what I wanted to do is I wanted to figure out the alpha n values, okay? So what we did was, we said the very first step I had to do was over here, right? I had to define what that waveform was. So basically what I said was x of t is equal to 2 for the first half of the period and equal to 0 for the second half of the period. And what I did was I set up in this equation. I said alpha n is 1 over t times the integral 0 to t. And I put in the waveform, the equation for the waveform that applies from 0 to t over 2. And then the equation for the waveform that applies from t over 2 to t. All right, what you see from that is that the second part of that equation went away, right? And then we went through and we evaluated, all right? And this was a pretty simple thing to evaluate. And what we ultimately ended up with is essentially alpha n equals 1 over j n pi times 1 minus e to the negative j n pi, okay? We talked through the details of that in the last lecture, so I'm not going to go through it again here, but that's basically where we ended last time. All right. Now, what I want to do is I want to graph the waveform now. I want to write some code in Matlab, because that's the kind of thing I'm going to ask you to do here on the homework. Is in the homework you're going to derive the alpha n values using the same sort of process like we just did on Tuesday. And I'm going to say, okay, well now I want you to graph that, to graph the waveform. So if I'm asking you to graph the waveform, so I'm asking you to graph that square wave, what function am I asking you to implement? Well, it's going to require a for loop, but the thing that I'm going to do is I'm going to be implementing this guy from negative infinity to positive infinity, okay? Alpha n e to the j n omega naught t, all right? I'm going to implement that in code. So how do I implement that in code? What do I have to do to implement that in code?
This is Fourier series.
Well, yeah, how do I do the Fourier series code-wise? If I want to draw that x of t, what's it going to take for me to do?
A for loop.
A for loop, right? And let's just kind of think that through for a second here. In fact, it's really going to take probably 2 sets of for loops, right? So the first loop, so let's say loop 1 will be to fill up the alpha vector, fill alpha n vector. All right. And then, and again, I'm just telling you one way to do this. The thing with code, there's always multiple ways to do it. You don't have to do a for loop. You can do a do loop or a while loop or one of those sorts of things. right? But there's different ways to do this. What I would say is, what I would do is I would fill an alpha n vector, and then I would create the x vector, okay? So when I say fill an alpha n vector, what I would probably do is I would say, well, I need to, so first of all, let's understand this. In the case of the Fourier series, this is what I got. And this applies for all n not equal to 0. Right? When I say this applies to all n not equal to 0, what is wrong with n equal to 0 here?
You'll get 0.
You'll divide by 0.
I'll divide by 0. Right? Now, as it turns out, I've got a problem with that, right? So this applied for n, basically for n not equal to 0. When n equal to 0, what frequency am I talking about when n equals 0? I'm talking about the
DC term, right?
DC term. So what frequency is DC?
0.
0, right. We always will handle the 0 term differently. Okay, we're always going to handle the DC term differently. And I'm going to get to that here today, but we're always going to handle the DC term differently. Okay, so for n not equal to 0, what I have right there applies. Now, what that tells me is how many different n values should I consider? Well, how many by definition should I be considering?
Minus the plus infinity.
Minus the plus infinity. So how many values is that?
Too many.
A lot.
Too many.
I mean,
too many,
when
yeah.
it reaches steady
Some
state.
people, I was waiting for somebody to say 2 times infinity. Yeah.
Times infinity.
Yeah, I don't know. It's a lot of values, right? And obviously I can't do that, right? So I just got to make a choice. Well, I'm going to do it for a certain number of them, and keep going, right? And see at what point, at some point, the waveform that I plot using my for loop should look pretty close to whatever the waveform was that what I was told. Okay. If I don't choose enough harmonics, it won't look right. I have to choose enough to make it look correct. Okay. So just to understand this here, let's go through the first part of this. All right. So I was given the alpha n is this right here. Okay. Was given that it was that. And so notice what I did here in my code. I start out with a clear all, as I always do, right? Because I want to make sure everything is 0. And then I set up, in this case, the fundamental frequency and the fundamental angular frequency. And then I somewhat arbitrarily said, I'm gonna use 10,000 points in a period. All right. So I did that. And then what I did was I just said, okay, I'm going to build up my alpha vector here. Now, what I've done is I've defined n equal to 2. So what does that mean here? Given what I've got on these 2 lines of code, which harmonics am I going to include, or which harmonic numbers am I including here?
-2 to +2.
-2 to +2. So that would be
Five.
-2, -1, 0, 1, and 2. Okay. And notice what I've done here in my for loop. I say for k equal from 1 to 1 to length of n complex. Okay. What I've done is I've said, okay, if n complex of k equals 0. So what is this? N complex of k equals 0. What is that checking? Yeah, I've got 2 conditions in my for loop, right? I've said, okay, well, if the n value, so n complex is what I'm calling the n value in this case, right? If my n value is equal to 0, what frequency am I at? DC. Okay. So what I've done here, notice, what is this statement here where it says alpha n and then it's followed by a 1 with everything in square brackets? What am I doing when I when I say the variable equals the variable with the number, with some number after it? What am I doing here on this line?
Concatenating that number onto the array.
Yep. Yeah, I'm appending that number to the end. I'm doing a concatenation. Okay. Now, in this case, I basically said when n equals 0, right? For the DC term, I'm adding the number 1 onto the end of the array. So I'm putting in the number that applies when n equals 0. Now, why did I know that was 1? Let me skip ahead here a little bit. How did I know in this case, how did I know that that value was 1? Looking at that waveform, I knew that alpha 0 was 1. How did I know that? Just because I know that?
Your amplitude is 2.
Because my amplitude is 2. So how do you think I would figure out the DC term? So what is the DC term always going to be?
An integer?
It's how much it's shifted up by. It's the average value of the waveform. Right? So if I had a pure AC waveform, that would be a waveform that had 0 average. So it spent half as much area above 0 as it had below 0. Okay, if you think of cosine or sine, think of sine for a second, right? Sine looks like that. What's the average value of sine?
0.
0. And the way you compute the average value for any waveform is you say the average value is 1 over t, 0 to t, x of t, dt. Right? I integrate over the whole thing and I divide by t. All right, so I integrate over a period. In this case, I don't even have to do an integral to do that. I could if I wanted to, but I can look at this. First of all, what is the meaning in this particular case or any case? What's the meaning of that integral? What does it mean to take an integral from 0 to t? What's the result of x of t integrated from 0 to t? What do I get when I take an integral?
Are you talking about getting a sum of all the parts that make up the function up from 0 to the period?
Yeah, and so when we talk about like a derivative is the slope of the curve at any given point, right? So
So it's the area?
It's the area under the graph. All right, the area under the graph. So in this case, if I'm looking at this waveform from 0 to t, what do I have to do? I just have to compute the area of this box here, right? So I could do an integral, or I could just say it's the area of that box times 1 over t, right? So 1 over t times what? Without doing any calculus, what times what?
Length times width.
Yeah, so 2 is the height of it. T over 2 is the width of it. And what do I get? 1. Okay, the 2's cancel, the t's cancel, and I get the number 1. This value is always my DC term value. Okay, that value is always my DC term value. So it's always the area under the curve. So if I go back here, all right, that's why I put the number 1 in there. All right, I just computed that by hand outside of MATLAB and put it in there. Okay, but what it really would be is the average value of the waveform. Now notice what I did. Else. All right, so I've got an else statement here. That else applies for what? When does that else apply in my code?
All other n besides 0.
All other n besides 0, right? So what am I doing? I'm doing an appending again, right? Alpha n, and then I append a value. And what I'm doing is I'm appending at the value of n that I'm talking about. I'm just putting in this equation right here. 1 over j pi n times that whole e to the negative j n pi. And so notice how I did that, right? I'm using this thing n complex of k, right? N complex was my n vector, all right, which goes from minus n to n. The reason I called it n complex and not n is because, as you might imagine, somewhere else in my code, I actually have an n vector, okay? So if you look at this, I go through that, and then at that point, I've created my alpha n vector. So the question then would be, how do I create the x vector? I want to look at what this x of t really looks like. So what I do is I implement this x of t right here. All right, I got to implement mathematically that function. Okay. So what I'm going to do is I'm going to create a for loop to do that. I just want to make sure everybody gets an idea of what's going on with that. So I'm going to do my for loop, let's say for k equal to 1. All right. For k equal to 1, what I'm going to do is I'm going to say that x is equal to whatever it was before plus what? What would I add in? If I did a for loop, so I'm going to run a for loop to try to create this thing. First of all, what vector would I be looping through when I make that loop? What vector am I running through?
Is it t?
Your n values maybe?
My n value, particularly my n values are my alpha n values, right?
Okay.
I need to make sure that x has a length of t. So let me back up for a second, right? All right, so nothing I heard there was bad, right? Basically, I need to make a t vector. All right, my t vector is going to be whatever length it's going to be. So in my case, I did it for a period. All right, and let's say I don't know what that time step is, but let's say I go for 1 period. Okay, then I'm going to create an x vector, which is empty, but has the same size as t. Okay, so it's loaded up, it's initialized, and it's all zeros. And then I'm going to loop through the alpha vector. So for k equal to 1, what I'm going to say is I want x to be equal to x. So this is all zeros at this point, plus what? What would I put in there?
Would it be the equation?
It's that equation, alpha n, right, times e to the j n omega naught t. All right. Except what I'm kind of doing here, and this is the thing I want to be careful about here, right? Is as I keep looping through. In fact, let me not do it as k. Let me do it as n, right? All right. So if I did this from n equal 1 to infinity, what I'm going to have to do is I'm going to basically keep looping through here, and I'm going to pull out a value of alpha, and I'm going to plug in a number for n. All right. And I'm going to just basically keep looping through this, and every time I loop through here, what am I going to do? I'm going to increment the value of n another number. So the second time through this guy, I'm going to basically take whatever I had for x before, and what am I going to do? Well, I'm going to basically add in whatever I need to when n equals 2. All right, and just keep going. Question? So x isn't like a vector, it's just a single number. X is a vector. All right, x is a vector, right? So notice how I made x. X is a zeros vector with the size of t. And when I every time I increment the harmonic number, I'm adding in another exponential value that has the same size as x, right? So this guy, e to the j n omega naught t, would have the same size as x. Okay, so let's look at the code for that here.
Professor, I have a question.
Yeah.
Our n and t aren't the same size, right?
Your n and your t are not the same size. Good. Yes, that's correct.
So how do they like function together?
Your n is the number of points in your vector of alpha values. So your n is the number of harmonics that you're considering, right? So your n. So I'll tell you what. Let's actually, rather than look at the code, let's actually look at my Matlab code. All right, and that way we can look at the output as it's created. All right, so I've got 2 versions of this guy. Let me see. Okay, so let's look at my actual code. All right. Now, here's where I loaded up my alpha vector. Here is where I'm loading up the x vector. So I made x is 0 size t. And what I do is I'm looping through the length of that n complex vector. Okay. So let's do this. Let me actually, I'm going to expand this a little bit, and I'm going to have it write out. This is how I like to debug stuff. If I want to know if I'm writing stuff out right, I'm going to have it spit out to the screen the K value and the N complex value. Okay. And notice I'm purposely not putting a semicolon because I want to see what happens when I do it. Okay. And yeah, I'm going to start there. Okay. Now, I am going to split the screen here. All right. And I'm going to run this thing here. And in this particular case, let's see, how many harmonics am I doing? I'm doing 10 harmonics. I want to do fewer than that. I want to do 1 harmonic. All right. So if I set n equal to 1, notice my n vector here. So I set n equal to 1. So what harmonics am I doing here based on what I've written out right here? What harmonics are going to be there?
3.
-1 to +1.
Yeah, -1, 0, and 1. Right. So there's so what that means, again, just in terms of this picture here, all right, in terms of what I'm showing here, if I have n equal to 1, then I'm going to have my n complex is going to be equal to -1, 0, and 1. Okay. So initially my x is a vector of zeros. Okay. And so I'm basically saying for k equal to 1 in steps of 1 up to n complex of, well, up to length of n complex. All right. Length of n complex. Like that. And what I'm going to do is, if I wanted to implement, my goal in this loop is to implement x of t equal to this summation. Now, I'm not actually doing it. Let's be clear about this. The equation is n equal -infinity to positive infinity. What am I implementing it from in this case? Where am I starting and where am I ending? In terms of the way that I'm writing this code, if n equals 1, what little n value am I starting at? Not negative infinity.
-1.
I'm starting at -1, and I'm ending at 1. And I'm basically saying alpha n e to the j n omega naught t, like that. Okay. And so the first time, so basically as I go through the loop, I want to say set x equal to that plus what? Help me out. How would I do this? Help me write the code. Okay, what equation? This equation, right? So what would I say? So if my alpha vector is alpha underscore n, what index of k? Okay, times what?
E to the j.
Exponential.
So yeah, exponential. What?
J times K.
Not j times k. J times, you're close. J
N complex.
times, yeah, whatever the value of n complex is at k, right? So think about that. The first time I go through this loop when k equals 1, what's n complex equal to? -1.
-1.
1.
-1. And I multiply that by t. All right, that's a bad multiply sign. All right, I multiply that by t. Okay, what's that?
Omega. I'm sorry.
And
did I miss-
omega, sorry, yeah, I forgot the omega. Times omega, and I guess I've been calling it omega naught. Sometimes you call the fundamental frequency omega naught. I'm not, that's the kind of thing, semantics, I'm not going to get caught up on that, but omega naught's what I call that very often. So, and I multiply that by t. So this guy has a length of t, right? He's the same size as t, right? So alpha n is alpha n of k is a single number, that's getting multiplied by a vector, right? And so as I go through this, I'm basically just continuing to, what is that? All right. I just continue to add stuff to that vector. You guys follow that?
Yep.
All right. That's for those of you who are not as comfortable with code, that I want to make sure that you guys follow that process, right? I'm just implementing this equation mathematically, all right, here. Okay. All right. So ultimately what I'm doing here is going through that process, and I can change the value of n that I use. When I want to debug, typically what I do, like what I was saying here, is if I want to know how this code is working, I'll have it spit out to me at the screen. What value, what's the current value of n complex, and what's the x vector look like at those points, right? I'll have it spit those out to me. Now, one thing I wanted to add here is notice I didn't necessarily have to do this, but I did. What did I do if n complex of k equals 0? So n complex of k equals to 0
Change the
means
index to the initial value.
No,
And
you
the-
just
the
take that.
DC
What's the
that's the
comp?
DC term. That's
Yeah.
the DC term. So what it says is multiply by a vector of 1s.
So I have a question.
Yep.
Is initializing your x vector before the for loop, is that necessary? Or is it just good practice?
I would, it's so much good practice that I'm not sure if it's necessary or not. The reason I say that is I don't ever want to start playing around with a variable that I haven't initialized ever.
Okay.
I'm not sure if MATLAB would have a problem with it if you ran this line of code and x didn't exist. I don't think it would like that. But I would always want to have it initialized so that I know what I'm beginning with.
Okay.
All right. So in this case, I have n equal to 1, so I'm going to run this guy. And there's what I get. Okay. So notice what I have. With n equal to 1, I just get a sine wave that fits right in there. All right. If I choose n equal to 2, all right. Now, n equal to 2 means I'm running from -2, -1, 0, 1, 2. Is it going to look any different? So Nate here in the room says it's going to look different. Anybody else have a different bet?
Wait, what was your question again?
I agree.
You agree that it's going to look different?
Well, I mean, as indifferent as the waveform itself, or
Let's run it. It looks exactly the same. Now, how does that square with what I said before? Now, I just said, I didn't prove, I just said, all right, here's if I added in one sine term. Here's if I added in a first and a third. Notice I didn't have a second, right? That's because something we talked about the other day, right? Where we ended the other day is we basically said, right? We basically ended the other day and we said, all right, this was the alpha n value that we had, right? So let's take a look at this guy for a second. We said this guy applies. Can I just copy that? I can't. All right. All right. We said the other day, our alpha n value is 1 over j n pi, 1 minus e to the negative j n pi for all n not equal to 0. Okay. The other day we started expanding that, right? I basically said if I have e to the j theta, what's e to the j theta always equal to? E to the j, what's Euler's identity say about e to the j theta? Cosine theta plus j sine theta. Which means if I plugged in a negative angle, e to the negative j theta, what's that become? Cosine of a negative angle is equal to what? Cosine of the same angle, right? And Sine spits out the negative value like that. Okay. So where I ended up with the other day is I basically started to apply this here. So I said I got 1 over j n pi times what? 1 minus, I'm going to plug this in here. So 1 minus cosine of n pi plus j sine n pi, like that. All right. So let's think about this guy right here. When n equals an even number, what happens?
Would the sign cancel out?
Well, so what's the sign? So if I have sine of 0 or pi or 2 pi, right? So think about what's going on. It's always, sine is always going to be 0 for if n is an even number. And if I had cosine of, so in other words, this guy would basically become 0 in that case. What about 1 minus cosine of n pi? So cosine of n pi, so what happens if I have cosine of 0 or cosine of 2 pi or cosine of 4 pi? What's true about all of those? What are they all equal to?
1.
They're always equal to 1. So I'm going to have 1 minus 1. So what's this? What's this guy? What's alpha n equal to if n is even? It's equal to 0. It's equal to 0. So if we look at what I just did here, when I said n equals 2, the second harmonic didn't appear because it doesn't appear, right? It doesn't exist, right? There is no even harmonics that appear in here. Now, if I went through and I said, what happens if n is odd? Okay. If n is an odd number, I would have alpha n equal to 1 over j n pi, like that, times what? Well, what's cosine of pi or cosine of 3 pi or cosine of 5 pi? What are all those? Those are all equal to minus 1. All right. Now sine of n pi is equal to what always? Sine of n pi is always going to be 0. All right. So this guy is going to become not 1 minus 1, but 1 minus 1 or 2, like that. So what that says is I only get in my response, my answer only has odd harmonics. All right, now in signals and systems, you learn all kinds of, there goes the podium falling apart again. In signals and systems, you learn all kinds of properties about waveforms. Well, if they're symmetric a certain way, then they have certain Fourier coefficients, and if they're symmetric a different way, they have certain Fourier series coefficients. I don't care about that stuff. I don't know why anybody would care about that stuff. What I care about is that you can figure out the alpha n values, and that you can relate that to sines and cosines. Okay. All right. Now what that says is, if let's change this n to 3. Okay. So now I'm going to go from -3, -2, -1, 0, 1, 2, 3. Is it going to look different now when I run the code?
I hope so.
You hope so.
I think so.
It will.
Code's always right, so yeah.
There it is. All right. What happens if n equals 4?
It would go back, wouldn't it?
They're going to go back. It's going to look the same as when n equals 3. Because adding in the fourth harmonic term.
Oh, it involves the third. Okay.
So there it is. All right. If I do n equal 5, now something else appears. All right. Now, one thing you could say about this, so let's just look real quick. If I can look at that alpha vector, so I can say alpha n. Boy, that's hard to look at, isn't it? All right. Let's do this. I can always make a figure here. I want to look at the values, and this is thing I've never taught you this command before, and I'm going to talk to you about it later. But I'm going to look at it this way: alpha n, the stem command. All right, we're going to talk about that command later, but the stem command is going to let me just see the values in that vector. All right, so let's see. So what I can see with this, all right, so n equals 0 is right here. This guy goes from -5 to 5. What it's doing is it's plotting the alpha n values. So you can see here when n equals 1, I've got a number. When n equals 2, I got a 0, right? Or I have 3 times 10 to the minus 17, what's basically 0. All right, when n equals 4, I got a 0. Okay, and I could keep going with this, and we could look at what that guy looks like. All right, but I wanted to show you, if you look at the even numbers, they're basically all 0. Okay. Questions about that? Probably lots of questions about that, but you don't even know what to ask yet. One thing it's a question?
No.
Okay, yeah, I shouldn't have. It's a comment, not a question.
Okay, buddy. I'll try
Right.
that.
So with n equal 5, when I run that, right, notice it doesn't, it looks kind of like the square wave, but not exactly like the square wave, right? Why doesn't it look exactly like the square wave? Well, because I haven't included enough harmonics, right? So if I included 99 of them, all right, now I'm going to run that. Take it a little bit longer. Hopefully not too much longer. Maybe a lot longer.
Uh-oh.
I don't think I've done anything too crazy.
You
Maybe.
might have ran out of RAM.
I don't think so.
So this would be an O of n squared equation, right? Since you have to do like 2 for loops inside of another loop from n to n.
I think that is.
So it would take a while.
It shouldn't take that long. Seems like it's taking longer than it should. It's not order n squared. I have to think about that. All right, there it's done. Doesn't seem like it should be order n squared, but yeah, I mean, because yeah, I guess it is order n squared. There it is. All right. It looks better. Notice it's got these ears that kind of develop here. There's a name for that called the Gibbs phenomenon. I'm not going to talk about that. It's not all that particularly important. All right. But if what we see is it's starting to look like the actual waveform, you'll always see this type of behavior usually at the edges, right? That it has these kind of what I think of as sort of ears that develop to it. Okay.
Is that something that we were looking at for project 1, the inverter?
No, I mean, okay, I see where you're coming from. With the inverter, in project 1, what you were looking at there is the fact that you had a real system that had some inductance and capacitance, and it was underdamped. This looks like an underdamped sort of response. It's not, it looks the same, but it's not the same thing.
Okay.
Yeah. Okay. All right. So in general, I will usually ask you to figure out alpha n values, because again, I think the math becomes a lot easier when you're figuring out the alpha n values. And this simplification that I did here, so what you could have done, and that's actually what I have in this comment here that I didn't use, was if you look at what I have here, I actually used the simplifications. And I did some stuff to say, well, if n is a even number, put in 0. If n is an odd number, put in this value. Now, that's a little bit beyond what I want you guys to be able to do in this class. But some of you guys who are computer engineers especially, hopefully you'll recognize the mod command. All right. But I didn't want to do it that way in this case. I just did it sort of by a little bit more brute force. There's more elegant ways to do what I did. All right, but that was a reasonable way to start. Okay. All right, so questions on what we did up to there?
I had a general question about the ears on the waveform. Do they ever go away if you go to an infinite amount of n values?
If you go to an infinite number of n values, they'll go away.
So it's just because we're taking some finite value of it.
It's
Because
anytime you do a finite value, you're going to get the ears.
okay.
Now, like I said, in a real system, you would never see those. All right, but in theory, they exist. But if you measure it on an oscilloscope, you would never see that kind of thing. I'm saying too much. Why would, because the world is, there's always an RC circuit that you don't see. There's always a low pass filter that you don't see. In other words, there's always filtering that's happening in nature that filters out high frequency things like that behavior. All right, that's beyond our scope here, but is a true statement. Okay. All right, now the other thing I guess that would be relevant potentially to what we might do in the homework is I might say, all right, well, find for me the other coefficients, right? So we said we've got these three different forms of the waveform. Most likely I'm going to ask you to compute the alpha values. I would never expect you probably to run through the AN, the BN, and the CN values, except to say that once you have the complex ones, you can very easily get back and forth between the others, okay? So we've got this picture here that I said, if I have the complex, I can always get to the other versions. All right, so knowing that, what we've gotten so far is we've gotten the alpha values. We basically calculated all of these values, and I want to do the other series. So how would I do that? So if I know the alpha values, so I know the alpha n values, the other series is the same waveform. X of t should be equal to C0 over 2 plus the sum n equal 1 to positive infinity Cn cosine n omega naught t plus theta n. And that should also be equal to A0 over 2 plus the summation of n equal 1 to infinity of an cosine n omega naught t plus the summation n equal 1 to infinity of the sine terms, right? So how would I calculate, if I know the alpha n values, how would I calculate the C of n, theta n, A of n, and B of n?
So you know that you can use C of n divided by 2 times E of your phase, right?
Yep. Yep, I can use these relationships here, right? That's probably
You
where I
already have
start.
like an omega and a t, and you know that's going to be the same.
Yep. Right. That's exactly right. So I can basically say, I can look at each of the alpha values, right? And I know the magnitude of the alpha value times 2 is the C value. I know that the angle of the alpha value is the theta value. Once I have that, I can easily get into this form of the series by just taking C times cosine and C times sine, okay? So to do that, all right, I wrote the code here, okay? All right, so notice what I did. So this is the same alpha setup that I did before. Didn't change anything about that. And then I initialized these empty vectors. Again, I always initialize. In this case, I didn't give them sizes. I just set them up as empty vectors, right? Whenever I write out AN equals square brackets like that, I've just made them empty vectors. They have nothing in them, okay? Then what I did here is I have a for loop that loops through the alpha vector. All right, now notice I created something different called alpha positive. We'll deal with that in a minute, right? But I loop through and I basically fill up the Cn and the theta n. Once I have the Cn and the theta n, I use the Cn and the theta n to calculate my A and B values, okay? Now notice here, I have a setup when k equals 1, I do something different than I do if k is something different. So let's look at what I've done here. So for k equal to 1 to length of n. So what am where's my n vector? Let's find that. What's different about n complex and n here?
Sorry, repeat that question again.
What's different between
Complex starts at negative value. and
n
starts at
complex
zero.
goes from a negative value to a positive value, right? Because in the complex form of the series, what do I always have to do? If I have a value at 1, I have to have a value at -1. If I have a value at 2, I have to have a value at -2. In the complex, or the just the sine and cosine version of the series, I start at DC, n equal to 0, and I go up to n. Okay, so that's the difference in this particular case, right? So notice what I've done here. When k equals 1, what's the frequency then? If I'm looping through the n vector, what's the first entry in the n vector?
0.
0. And when n equals 0, what's special about n equals 0?
DC term.
DC term, right? DC term. So notice what I did here with the DC term. Well, there never is a b of 0 value. Now, what I did here was I said a of 0 is equal to 2 times the absolute value of the alpha value and 2 times the absolute value of the alpha value. Okay. Now, I didn't necessarily have to do absolute value, all right, but I did, and I should be careful. And technically, I'll just keep it that way. All right. If you look at what I've done here by two times that value, right? If you look at the equation we have for the series, right? That fits with the equation we have for the series here, right? Because we take the DC, this is always tricky for people, right? Is the DC term of the series, alpha 0 is like this. Always. Alpha 0 is the DC value. A0 is twice the DC value. C0 is twice the DC value. Dumb, I wouldn't have done it, but that's the way it's done. Okay? It just leads to confusion, but that's what I've done here. Okay? Now notice down here, if it's anything other than n equal to 0, meaning anything other than the first entry in the n vector, here's what I have. Notice what I've done. I've taken the magnitude of the alpha value, the angle of the alpha value, and then c times cosine, negative c times sine. And that's how I convert between the series. Okay? If I run this, take it a second here. All right? I've got 3 series on top of each other right there. All right, all 3 of them are plotted on top of each other. There's my actual plot command at the very end of it. Now notice what I've done here is basically in this block right here, line 57 to line 66, what am I implementing here? Like right here, what am I implementing on these 2 lines, 62 and 63?
The phase form and then the cosine and sine.
Yep. So basically I'm doing the same thing. I'm creating my A and B vectors and C vectors and theta vectors. And then I'm basically going through the for loop to make the same plot. And one good check is it better be the case that if I've done my math right, all 3 of them better be the same, and they are, okay? So in this particular case, all 3 of them are sitting on top of each other, okay? And if I change the n here, that'll change it. So I'll make it 9, right? And it'll get closer. There it is. All right, and there's actually, like I said, there's 3 things sitting on top of each other in there in the series, okay? That's really all there is to it. So one of the things about this and why I think this is good exercise is it gets you guys in used to writing some code, right? This is some good things to think about when it comes to beefing up your coding skills, all right? And how to...
Is this what we'll be doing for the homework 8 then, or?
Homework 7 will have some of this stuff, yeah. So in homework 7, you can guess a lot of the problems you're going to have are basically going to be like, okay, so in this case, I had a square wave, and I computed the alpha value for the square wave, and then I plotted that. I'm going to ask you to do the same sort of thing, right? you're gonna have to do the calculus to figure out what the alpha value is. You're gonna have to tell me the alpha vector. You're gonna have to tell me the A vector, the B vector, the C vector, all that stuff. Make sense?
Yeah,
Not
sure.
yet. It does in theory until you do it, right?
Yep.
Everything makes sense until you do it. All right. That is all I have for today. Basically got 2 minutes left. Any questions you guys want to ask?